start, sir? Krishnan, sir?
Yes, yeah, okay. Yes, Smriti, yeah.
Okay, sir. स्वागतम, शुभ स्वागतम, आनंद मंगल मंगलम, नित्य प्रिय भारत भारतम, अथ स्वागतम, शुभ स्वागतम। भारतीय स्वतंत्रता के गौरवशाली 75 वर्ष के उपलक्ष्य में मैं आप सभी को इस आजादी के अमृत महोत्सव की बधाई देती हूँ। हमारे संस्थान के 60वें स्थापना दिवस समारोह के इस उल्लेखनीय अवसर पर मैं आप सभी का स्वागत करती हूँ। आज के समारोह के लिए पधारे गणमान्य अतिथियों से अनुरोध करती हूँ कि कृपया वे इस वर्चुअल मंच पर हमारा स्वागत एवं अभिवादन स्वीकार करें। माननीय सचिव पृथ्वी विज्ञान मंत्रालय डॉक्टर एम रविचंद्रन, कार्यक्रम के मुख्य अतिथि प्रोफेसर वीके दधवाल, कार्यक्रम के विशिष्ट अतिथि प्रोफेसर वी रामास्वामी, प्रभारी निदेशक एवं वैज्ञानिक जी IITM डॉक्टर आर कृष्णन, वरिष्ठ वैज्ञानिक डॉक्टर पी मुखोपाध्याय, संस्थान के प्रशासनिक अधिकारी श्री अजीत प्रसाद जी, समस्त IITM एवं MOES परिवार एवं उपस्थित सभी श्रोतागण, मैं इस आभासी मंच पर आप सभी का हार्दिक स्वागत करती हूँ। देवी सरस्वती ज्ञान का प्रकाश पुंज हैं और ज्ञान अज्ञानता रूपी अंधकार को दूर करता है। हमारी परंपरा के अनुसार हम ज्ञान की देवी सरस्वती जी को नमन करते हुए कार्यक्रम का शुभारंभ करेंगे। इसके लिए मैं मेरे सह संचालक श्री भूपेंद्र बहादुर सिंह, वैज्ञानिक डी, को आमंत्रित करती हूँ कि वे सरस्वती वंदना प्रस्तुत करें।
या कुंदेन्दु तुषार हार धवला, या शुभ्रवस्त्रावृता, या वीणावरदण्डमण्डितकरा, या श्वेतपद्मासना, या ब्रह्माच्युतशङ्कर प्रभृतिभिर्देवैः सदा वन्दिता, सा मां पातु सरस्वती भगवती, निःशेषजाड्यापहा, शुक्लां ब्रह्मविचारसार परमाम्, आद्यां जगद्व्यापिनीं, वीणापुस्तकधारिणीमभयदाम्, जाड्यान्धकारापहाम्, हस्ते स्फटिकमालिकां विदधतीं, पद्मासने संस्थितां, वन्दे तां परमेश्वरी भगवती, बुद्धिप्रदां शारदां, वन्दे तां परमेश्वरीं भगवती, बुद्धिप्रदां शारदाम्।
कार्यक्रम की इस मधुर शुरुआत के लिए भूपेंद्र जी को धन्यवाद देती हूँ। अब मैं अनुरोध करती हूँ डॉक्टर कृष्णन से कि वे इस सभा में अपना स्वागत उद्बोधन प्रस्तुत करें। सर, कृपया स्वयं को अनम्यूट करें एवं संबोधित करें।
धन्यवाद स्मृति जी। It gives me immense pleasure to welcome Dr. M. Ravichandran, Honorable Secretary, Ministry of Earth Sciences, Government of India. Chief guest of today's function, Professor Vinay Dadwal, former Director, Indian Institute of Space Science and Technology, Thiruvananthapuram, presently Indira Gandhi Chair Professor, National Institute of Advanced Studies, Bengaluru, and member of IITM Governing Council. Guest of honor for today's function, Professor V. Ramaswamy, Director, Geophysical Fluid Dynamics Laboratory, Princeton, USA. All the former directors of IITM, Professor R.N. Keshavamurthy, Professor B.N. Goswami, Dr. M. Rajivan, and Professor Ravi Nanjundaya. All the former secretaries of the Ministry of Earth Sciences, distinguished dignitaries, special invitees, all the present, past and present members of IITM family, MOES family, friends, ladies and gentlemen, I welcome you all to the IITM's 60th Foundation Day celebration. Since its inception in 1962, IITM has been functioning as a national center for basic and applied research in tropical weather and climate system with special reference to the Indian monsoon and striving for betterment of weather and climate predictions through value-based research and providing research support to the National Weather and Climate Services. Through sustained research over the last 6 decades on various aspects of the tropical and global climate system, IITM has gained multifaceted expertise in understanding the atmosphere, ocean, land, cryosphere, biosphere interactions of the coupled climate system, and the same has been successfully translated into improved weather and climate forecasts on different spatial and temporal scales. Today, IITM is among the top centers of excellence worldwide in terms of basic research on the coupled climate system, as well as weather and climate modeling and forecasting, including monsoon predictions on different spatio-temporal scales, which have been widely recognized and appreciated. The Institute's scientific expertise has wide range of applications for agriculture, water resource management, health, transportation, communications, economy, etc. Currently, IITM is focusing on major thrust areas in tropical weather and climate, including monsoon prediction at different scales, climate change research and projections, physics and dynamics of tropical clouds, thunderstorm dynamics and atmospheric electricity, air quality research and forecasting, airborne atmospheric research, academic and training activities. Many of the weather and climate forecast products developed by IITM have been handed over to IMD for operational forecasting. I would like to highlight some of our R&D activities during the last 1 year. The IITM Earth System Model, also known as the IITM ESM, is the first global climate model from India that contributed to the Coupled Model Intercomparison Project, 6th phase, also known as CMIP-6 experiments, and the recent IPCC Intergovernmental Panel on Climate Change, IPCC Working Group 1 6th Assessment Report, published on 9th August 2021. Also, IITM scientists from the Center for Climate Change Research were engaged with the IPCC AR6 process as lead authors, chapter scientists, and reviewers. Currently, there are ongoing efforts to develop the next generation IITM Earth System Model and global high-resolution climate projections at 27-kilometer grid. High-resolution forecasts of tropical cyclones using the GEFS T1534, that is a 12-kilometer grid resolution, which is the highest resolution based on 23 ensemble members, have provided forecasts of tracks, strike probability, intensity, and landfalls of tropical cyclones Tauktae and Yas, very severe cyclones, and Shaheen with skillful accuracy. These forecasts have been extensively utilized by IMD in generating the final operational product. The GFS-based ensemble prediction system showed higher accuracy than the deterministic GFS forecast. Initial work on the next version of extended range prediction system based on a multi-physics, multi-model ensemble shows appreciable improvements in predicting the large-scale, low-frequency variability signal and weekly mean rainfall up to 3 weeks in advance. IITM has successfully completed the generation of 40 ensembles of long-term, that is 21 years, coupled ocean atmospheric analysis using CFS V2 local ensemble transform Kalman filter, also known as LETKF, weakly coupled data assimilation system for the period 1999 to 2019. Seasonal predictions of the Indian summer monsoon rainfall using the weakly coupled data assimilation system show better skill than the forecasts initiated from the CFS initial, that is CFS reanalysis initial condition, with a gain of 1 month predictive lead time. Also, preliminary results of Antarctic sea ice simulation in IITM CFS V2 suggest a relatively better depiction of sea ice extent over the Antarctic region. IITM provided support to IMD for operational long range or seasonal forecast of the 2021 southwest monsoon. Flood forecasting system for all the river basins of India has been developed and shared with Hydromet division of IMD for operational utilization and application. The hydrological forecasts are based on bias-corrected GFS quantitative precipitation forecasts. With the kind approval of Honorable Minister of Earth Sciences, IITM has signed a new agreement with the World Meteorological Organization (WMO) to host an International Monsoons Project Office (IMPO) at the Institute, initially for 5 years with effect from 30th July 2021. IITM has successfully implemented the operational fog early warning system for the IGI Airport, New Delhi and northern region of India. A new 21-member ensemble fog forecasting system has been developed for predicting the probability of fog occurrence. An air quality early warning system was developed at IITM and officially handed over to IMD for operational implementation in July 2021. Also, a decision support system for air quality management in Delhi National Capital Region has been set up, which was recently launched by the Honorable Minister of MOES, Dr. Jitendra Singh, on 18th October 2021. An atmospheric research testbed site is being established in central India near Bhopal. The civil and electrical works have been initiated and a C-band radar has been installed there. An observational campaign during the 2021 monsoon season was conducted for collecting data on convective and microphysical properties in the monsoon core zone for the first time. For the CAPEX, that is the Cloud Aerosol Interaction for Precipitation Enhancement Experiment, Phase 4 at Sholapur and Tuljapur sites, all the ground-based observations and radio sonde measurements are being carried out at Tuljapur site without interruption. A special radio sonde observational campaign is initiated at Sholapur to validate wind products from wind profile observations at Sholapur and Tuljapur. In addition, with IMD, IITM continued to utilize thunderstorm dynamical prediction system for detection and prediction of severe convective systems and lightning occurrences during the pre-monsoon and also monsoon seasons of 2021. In addition, several interesting scientific investigations were undertaken during the last year, which include high-resolution reconstruction of the Indian summer monsoon record for the past 3,200 years using oxygen isotope analysis of speleotherms from Kadapa, Andhra Pradesh. This is very high resolution, almost on an annual scale from Kadapa, Andhra Pradesh. And there were several climate change studies on extreme precipitation events, tropical cyclones, sea level rise, monsoon response to anthropogenic drivers like greenhouse gases, aerosols, land use, land cover change, and so on. Decadal climate variability and ocean atmosphere coupled interactions were also studied, and many papers came out during the last 1 year. Observations and modeling of atmospheric chemistry processes over the southern Indian Ocean and Antarctica and climate connection studies have also been started. A global scale emission inventory of dimethyl sulfide, which is a climatically sensitive trace gas, has been prepared. Observations and modeling of trace gases in the upper troposphere, lower stratosphere, also known as the UTLS, of the Asian summer monsoon and their climatic implications were investigated. Ocean biogeochemical processes and carbon cycle experiments were also studied. In addition, cloud aerosol interaction and precipitation mechanisms over the monsoon environment were studied. Likewise, the role of land atmosphere interactions and soil moisture variations on the Indian monsoon variability has also been studied. Lastly, modeling of mesoscale convective systems over the eastern Tibetan plateau using convection permitting high resolution model at 4-kilometer grid. Regional climate model experiments were conducted. This is part of the WCRP Cordex flagship pilot study. And there are many more interesting studies that were undertaken during the last year. MOES has approved the establishment of a virtual center for development of artificial intelligence and machine learning at IITM Pune in order to expand the domain through multidisciplinary programs in the field of Earth System Sciences. This virtual center will coordinate with the units of MOES to identify problems that can be addressed with AI/ML tools, and will also plan and advise strategy to develop AI/ML based application tools. IITM successfully organized the 18th International Conference on Clouds and Precipitation, ICCP 2021, virtually with more than 200 oral presentations and 400 posters from across the world. This is a very big conference. And IITM has initiated the process of atmospheric research using unmanned air vehicle UAV. Clearances and permissions are obtained from the Airport Authority of India, the Indian Air Force, and conditional exemption from the Ministry of Civil Aviation for using UAVs and drones by IITM Pune for atmospheric research. Also, there has been a setting up of atmospheric weather radar network, which has been initiated. IITM has signed an MOU with Suzlon Energy Limited, a private entity, for the potential collaboration in the field of mesoscale modeling in both forecast and hindcast mode, as well as rain forecasting. IITM has signed MOUs with Cotton University, Guwahati, and Commissioner of Disaster Management, Government of Tamil Nadu, for work related to thunderstorm and lightning. With 83 sensors across the country, lightning location network has been established, and a map of lightning prone areas has been prepared and shared with the National Disaster Management Authority. Under the Azadi Ka Amrit Mahotsav celebrations, various activities are being organized to showcase IITM's achievements and research and development activities. Despite the pandemic conditions, there were sustained efforts from IITM to ensure proper training and human resource development through DESC, that is the development of skilled manpower in Earth System Sciences and academic cell. I am happy to inform that in IITM we could publish 227 peer-reviewed papers in reputed national and international journals with cumulative impact factor of 836 during the financial year 2020 to 21. In the calendar year 2021, we have published more than 220 papers with cumulative impact factor of 946 so far. I express my sincere thanks to all of the IITM frontline employees for relentlessly providing uninterrupted services during the challenging times of COVID. I also thank admin and GA for successfully conducting and arranging vaccination drives, which have greatly benefited all of us. Whatever has been achieved so far has been possible only with the collective efforts of all the scientific, technical support and administrative staff of IITM. In particular, we greatly acknowledge and appreciate the strong support from the Ministry of Earth Sciences, which has been the backbone for all the scientific research and development work at IITM. I am very optimistic that we will sustain our sincere efforts with energy and vigor, and also enhance the scientific collaboration of IITM with all our sister MOES institutions, plus various universities, academia and scientific institutions, with the endeavor to reach greater heights and strengthen our country's weather and climate services for societal benefit. On this Foundation Day, on this 60th Foundation Day of IITM, I welcome all of you, and let us rededicate and pledge ourselves to strive hard for making our institute more successful and become a world leader in our field. I thank you all once again for your great support. Jai Hind.
Thank you, Dr. Krishnan, for your inspiring and encouraging words, and also for highlighting the significant achievements of IITM. It is indeed an honor for us to be associated with this great institution. Moving ahead, we are delighted to have with us Honorable Secretary, Ministry of Earth Sciences, Government of India, Dr. M. Ravichandran. Dr. Ravichandran held several prominent responsibilities including the Director NCPOR Goa, where he played instrumental role in execution and implementation of polar science activities of India and geoscientific exploration of non-living resources and survey. He has been in charge of coordinating several of India's scientific missions to the Antarctica and the Arctic. As the Deputy Project Director, Indian Argo Project, while being at INQUISE Hyderabad, he formulated and executed the project and also implemented the ocean data assimilation and modeling for operational ocean services. An avid researcher himself, he continues to motivate the climate science community. Recently, he has been appointed as the Secretary, Ministry of Earth Sciences, a well-recognized figure in the country. He doesn't need any further introduction. May I now request Honorable Secretary to deliver opening address. Sir, you may kindly unmute yourself and start your lecture.
Thank you, Pivendra. Today's chief guest, Dr. Datwal, former director of IIST and also now Indira Gandhi Chair Professor of NIAS. Guest of honor, Dr. Ramasamy, Director GFDL NOVA, Dr. Krishnan, IITM Director, all the former directors of IITM and former secretaries of MOES, colleagues from IITM and friends and all invitees, very good afternoon to all of you and very good morning to Dr. Ramasamy. It is my great pleasure to participate in this 60th year of Foundation Day of IITM. First and foremost, I congratulate the team IITM for your enormous contribution to the nation. IITM has made significant contributions, especially during last 1 decade, to improve the prediction system and also understanding weather and climate processes. On this Foundation Day, I should not miss thanking the founders of IITM, right from Dr. Bishareddy to Professor Ravi Nanjundaya, who have made enough contribution to the growth of the IITM journey, including the vision of imparting scientific knowledge to the society. Their contributions are greatly acknowledged. Of course, you all know that IITM has publication has a great record in the recent years, and also I place it on record. This IITM library also is a role model for MOES. I'm also happy to note that I started my career from IITM. I feel privileged to be from IITM. IITM mandates, actually it starts from right from observations, understanding, and model them to better prediction of weather and climate. Of course, many points already Dr. Krishnan has outlined. The important one is the monsoon dynamical predictions. Of course, they started from seasonal prediction, extended range, and also improving the physical parameterization scheme and other things, also important contribution from IITM, and which we need to improve further. Also, the climate variability and predictability and its application, also one of the important area which IITM is mainly concentrated on. I think we have to work on more. And in the observation aspect, understanding the cloud better and incorporating the same in the model, I think a lot of process-specific observation is in need of the hour. Already you have made many observation campaign like KIPEX or High Altitude Cloud Physics Lab or a thunderstorm or lightning dynamics and various observations, radar and satellite meteorology. So many observations are in place. I think it is a time we need to understand much more, especially the cloud processes and cloud parameterization scheme and other things we have to improve. Of course, IITM role in training and capacity building is very important contribution from IITM. It is not only for IITM, it is for all the Ministry of Earth Sciences. The infrastructure in place in HPC, I think, and also the other airborne lab and maybe the new lab of Popal lab and other things will definitely improve the scientific contribution by IITM. Though our understanding has significantly improved for the forecast system, but we need to do much more. I am extremely happy and congratulate IITM for the contribution to IPCC, but we need to do much more in incorporating or improving not only physics component, but also chemistry in the atmospheric model or biogeochemistry model in the ocean. Also, we need to understand and improve the interaction between the tropics and poles, especially polar interactions, CIs or CIS dynamics in the global Earth system model. Of course, in order to improve the forecast system, we need to mount or focus a new phase, need a transformative change. So up to now, we have set up the model, we are able to predict the system, or we are able to provide the sufficient forecast and other things, but we need to improve. For that, we need to go something new dimensions. So I personally feel that there are three areas which we need to concentrate. Maybe you know better than me. I feel that one is we understand most of the linear systems, what is in the monsoon or any weather system, but many non-linear system yet to understand. So at least whatever we need to understand, I think we have to, the non-linear system we need to understand and incorporate them in the modeling system so that we can significantly improve. And the second thing is, I think the resolution is one part, and data assimilation, the more data assimilation of the data and more improvement of the model and other things, forecast will be better. But at the same time, we also need to focus on parameterization of clouds in the atmospheric model, or maybe the mixing scheme in the ocean, which need to improve, and we need to put more effort on that directions. And also whatever we know the science, maybe we have to incorporate some of the remote forcing, which is not able to capture, which is observed, that we need to maybe some of the forcing recently, it is known Atlantic influences, or some of the polar region contribution to the tropical weather, which need to be incorporated properly in the model. Also, when we talk about internal dynamics and external forcing, I think still we need to understand a lot more in understanding our internal dynamics of the system. These are some of the things which we need to focus on it. And while congratulating the team IITM, I look forward to more contributions from IITM for better predictability. IMD is an operational agency, and they heavily depend on you to improve the forecast system in all time scales. We should have constant interactions and discussions with other centers of MOEs and also involve academia. It is imperative that we need to strengthen our international collaboration for better understanding for basic science as well as for the applied science. Foundation Day is also the day when the past, present, and future of the institution come together, taking vows to uplift this institute to the greatest possible height and dimension. I am absolutely sure that with your commitment, support, and contribution, IITM will scale new heights in the years to come. We need transformative change. I wish to assure that positive and productive ideas will be nurtured and encouraged. I extend my warmest greetings on this occasion. Once again, I wish you all happy Foundation Day. Thank you.
Thank you, sir, for extending your warm wishes and support to IITM on this important occasion. This will definitely keep our spirits high to meet the aim and vision of the ministry that has been entrusted to us. We are blessed to have distinguished personalities to address us today. It is my privilege to introduce the chief guest of the today's program, Professor Vinay Kumar Dadwal, former Director, Indian Institute of Space Science Technology, Thiruvananthapuram, presently Indira Gandhi Chair Professor at National Institute of Advanced Studies, Bangalore, and Member Governing Council, IITM Pune. Professor Dadwal has been instrumental in guiding several researchers of our generation. He is a renowned name in the field of Indian remote sensing, agriculture, carbon cycle, and environmental science studies. He obtained PhD from Indian Agriculture Research Institute in plant physiology. Working in Space Application Center, ISRO, he was the head of Crop Inventory and Modeling Division. He had been the Dean of Indian Institute of Remote Sensing, Dehradun during 2004 to 2010 and concurrently Director in charge of UN Center for Space Science and Technology in Asia and the Pacific. He was the director of National Remote Sensing Center ISRO during 2011 to 2016. His major achievements are in the area of Earth observation applications. This includes developing techniques for crop forecasting using Earth observation, and while at NRSC, realization of National Geospatial Portal Bhuvan, National Database for Emergency Management, National Information System for Climate and Environmental Studies, Space-Based Input for Sustainable Development and Planning, Water Resource Information System, Disaster Management Support System, and more. And in satellite data, acquisition and processing, including realization of MGOs and ground station at Antarctica. While at IIRS, he had been responsible for strengthening field-based and quantitative application of remote sensing and adjacent-based certificate program in the field of remote sensing. His scientific contributions include as Project Director, National Carbon Project during 2007 to 2016 in Biogeochemical Cycle of Carbon for India and in diverse Earth observation application areas as agriculture, crop simulation models, forestry, geohazard, geoinformatics, hydrology, land cover land use, land surface processes, meteorology and oceanography, and has contributed to more than 300 peer-reviewed papers and co-guided 10 PhD students. He has extensive international cooperation experience as a member and leader of Indian delegation to UN Committee of Peaceful Uses of Outer Space Vienna during 2013 to 2015, in its Scientific and Technology Subcommittee during 2013 to 2016, and was the chair of the same in 2016. He has been member and co-chair of Indian delegation in international cooperation meetings with US, Japan, ESA, and China. His scientific program management experience includes co-chair National Spatial Data Infrastructure of DST during 2011 to 2016, member Governing Council of Indian National Center for Ocean Information Services IITM and many state remote sensing center, as well as in research and scientific advisory committee of National Atmospheric Research Laboratory Gadanki, National Rice Research Institute Cuttack, Space Physics Laboratory, VSSC, etc. He also served as government nominee in the board of Antrix Corporation and chaired the Project Advisory and Monitoring Committee of DST Network Project on Imaging Spectroscopy and Applications. He has been awarded with several awards like ISRO Outstanding Achievement Award, Bhaskara Award, Satish Dhawan Award, Hariom Ashram Prerit Dr. Vikram Sarabhai Award for Space Applications, ISRO Merit Certificate, ISRO Astronautical Society of India Award for Space Applications, Indian National Remote Sensing Award, and more. Sir, we are grateful for your presence and thank you for gracing this milestone day of our institute. I request Chief Guest Professor Dadwal to please present his address to this gathering. Sir, you may please begin your address.
Respected Dr. M. Ravichandran, Secretary, Ministry of Earth Sciences, and of course, congratulations on being given this very important responsibility. Dr. Krishnan, currently the Director of the Indian Institute of Tropical Meteorology, Professor V. Ramaswamy, Director, Geophysical Fluid Dynamics Laboratory, Princeton. Sir, you head the laboratory where Saikuro Manabe developed the first three-dimensional atmospheric model, along with the GFTL founding director, Joseph Smagorinsky, which has been awarded the 2021 Nobel Prize in Physics. So it's a very happy occasion to have you in midst of us. Dr. Partha Mukhopadhyay, all the invitees, guests, well-wishers, members of IITM family attending the today's online Foundation Day event, ladies and gentlemen. Good evening to all Indian colleagues, good afternoon for friends from Europe, and good morning to Professor Ramaswamy and others who may have joined from America. I consider it to be a singular honor and privilege that I have been asked to, participate in the 60th Foundation Day. 60 is a very round number. In government service, you actually stop working But I believe for an institution like the IITM, 60th Foundation Day is a springboard for future achievements. And we are having this function in a unique manner in the presence of a new Secretary, Ministry of Earth Sciences. Meteorology, atmospheric science, climate, they are all important to human society, we need not say. But if you really see what has been happening past couple of days and months, it has become a topic of because of climatic extremes, because of challenges in air quality, because of what has been happening at COP26 at Glasgow, which basically is related to the future of the human society. So this subject is now brought to the center stage and then concerns everybody. So obviously, the demand on the practitioners of meteorology and especially the IITM, because IITM in its vision, it says it will provide the leadership, including the global linkages, and support the Indian efforts in atmospheric science and meteorology. So the demand on it are going to be very, very large. So this is, I think, a very appropriate time to look at what are the likely challenges. And I think it is also nice to remember all that has been achieved. Dr. Krishnan has elaborated on it. So I do not intend to really count on the achievements, except I would like, as a non-meteorologist amongst this galaxy of atmospheric scientists, I would be definitely like to share my perspective with few remarks. But let me also recall my association with IITM. Thank you for very kind introduction, but I would like to, share with all that after doing my PhD, as was told, I started my research career in Space Application Center, Ahmedabad. SAC Ahmedabad, the remote sensing group, has a very special link with IITM, as Professor Pisharotti, the founding director of IITM. He also was the founding director for what was then in 1969 the Remote Sensing and Meteorology Division. The four divisions which existed in the pre-ISRO era before 1972, they were all combined to really establish Space Application Center in 72. So in a sense, he was the founding director of the remote sensing activity. Also, he was the founder of the first experimental study in remote sensing, since he conducted a coconut wilt experiment with a helicopter platform in Kerala with a color aerial infrared film, which had the collaboration of Dr. Sumanwar and Professor Swaminathan, the agricultural scientist. I think we can return to the linkages later. I also had the opportunity to work with the past directors, listen to them, and had been in committees like Monsoon Mission, CTCZ, MetFlux, and so on and so forth. And they have always been gracious enough to invite me for the seminars and meetings, because two things. One is, I think, the current day meteorological research does depend on the space data. So there are now two dimensions. One is the space data of the future, and the second one is my area of work, which is how to provide relevant and appropriate boundary layer to really simulate through your field what is happening to the atmosphere. I still believe this field requires much more focused attention than what has been made available, although a brief mention was made of monitoring the soil moisture, right? But coming back to the entire area of the sphere of IITM and its importance, there is no doubt that in the past 6 decades, it has definitely delivered to all the expectations of its founders. It has also responded well to the changing requirements, whether they are from the IMD, they are from its administrative ministry, which provides funds, the societal requirements, the international community collaborative requirements, and the entire scientific community of researchers and practitioners in the field of meteorology, atmospheric, and climatic science. So, as a public funded research body, where in India there is a change in focus of how India would be conducting its science in future. So one example is, I think in the last 1 year, it has been brought, very vividly to the attention that the government has decided to open the entire space to private players. It also has opened its facilities. It also is now supporting the startups and a large number of new initiatives by private and commercial enterprise in space technology. I think some of this wind will blow in the field of atmospheric science and meteorology also. I read that in US they have NOAA perhaps has decided that they will commercially purchase space data from private players. I also understand that new observation networks by private players for atmospheric science is being built at a couple of places. So IITM now has the challenge not only to retain its leadership and the pivotal role, but it also has to be ready for changes that may happen because of the policies, because of the need to really accelerate our scientific output, the need to really link the science with the society and various applications. Services may actually be done by private players, but then somebody would really have to work with them and then help them in creating such type of applications. So this is one such area. But let me in general talk about the atmospheric science does require observational network. It requires modeling expertise. It requires long data archive. And it also requires active collaboration with a large number of group with various specialization. So the IITM strategy, I'm sure it will look to develop instrumentation capability both for ground, aerial, and space platform. I was very much happy to learn that the use of UAV has been proposed and the various approvals are also in place. But then the approval and the logistic part is one, but then building your own sensors and developing them, and then at some stage these sensors they are qualified enough to move to space, I think would require some in-house work as well as having the capabilities and collaborations with various other organizations. In the past decade, we have seen how the IITM has got the leadership in the computational infrastructure. The issue with the computational infrastructure is a leader has to continuously run to remain a leader. So because it is likely that your facilities of I think 11 petaflop, etc., may likely get overshadowed by somebody else who requires more. And obviously, this also is inadequate for the next level of challenges. So now I think in addition to the atmospheric science, you have to engage with computer specialists to see whether you would scale in the same way or you would have more cost effective, more efficient and more powerful, yet more powerful computational systems in the future, which will meet your requirement. It's also very gratifying that there have been campaigns to collect various observations in various parts of the world, including oceans, and that too with international community. But now IITM would really get a super instrumented site in Bhopal and would then also collect long-term data on various parameters, which are dozens of parameters. So which is a very, very happy sign that more fundamental research would get done. One issue I think which also has sometimes helped me is, look at it. IITM in past had great leadership in various specific discipline. Of course, two people who passed away very recently include Dr. Sikka and Dr. Pant. Now, how do we generate the next generation of experts in that discipline, or whether some disciplines would really eclipse due to superannuation of your global experts? This is, I think, this is a challenge which then IITM really has to look at it. So not only it has to engage more with various application experts and themes, it also has to ensure that whatever the in-house expertise and these skills are developed are not lost so that they have to be redone. It really is very good that it has a better observational structure, infrastructure. It is also moving into having a UAV and other type of observations. Now, the challenge is how much fund and human resource would this require? And what would be the ways to really get this? Most likely, the ministry and Dr. Ravi Chandran will support it amply and suitably. But are there some other models? Because slowly, I believe the funding pattern for research, the engagement with the community, as well as with young researcher will change. So, but what I am sure and very clear is that IITM would continue. It would continue to really perform admirably in research. It has been told by Dr. Krishnan, we have for the first time Earth system model. We also have so many other things. But now I just wish to point out that the future challenges are not only to continue this, but new type of challenges which the IITM community will face. And I'm very clear in my mind that there is a set of very well distinguished and capable people who would really come up with the solutions. And I wish them everybody well. And you can always count me as a friend, as a well-wisher, as a family member to help in all activities of IITM. Thank you and congratulations on your 60th Foundation Day. Thank you.
Thank you, sir. Thank you very much.
Thank you, Professor Dadwal, for inspiring words and suggestions. Your kind presence and address have set the tone for today's program. Now, I would like to take this opportunity to introduce the guest of honor of today's program. We are honored to welcome Professor Venkatachalam Ramaswamy, Director, Geophysical Fluid Dynamics Laboratory, Princeton, USA. Professor Ramaswamy received his PhD in Atmospheric Science from State University of New York at Albany and bachelor's and master's degrees from the University of Delhi, India. He joined GFDL as visiting scientist in the year 1995 and later on held the positions of physical scientist, group leader for middle atmospheric sciences, and senior technical scientist. In the year 2008, he became the fourth director of the GFDL. His research career has focused on improving our understanding of atmospheric physics and the roles of natural and human-induced factors driving climate change by developing and using state-of-the-art climate models. He has published over 180 high-impact papers in referred journals. He has mentored several graduate students, postdoctoral, and visiting scientists. From 1992 to 2021, Professor Ramaswamy has been a lead author, coordinating lead author, or review editor for each of the major assessment reports of the Intergovernmental Panel for Climate Change. He has also been a coordinating lead author on the World Meteorological Organization assessments on stratospheric ozone and climate, and the first US climate change science program. He is fellow of the American Geophysical Union, American Meteorological Society, and the American Association for the Advancement of Science, and has been recently elected as fellow of the American Physical Society. He has also been involved in the leadership of the US Global Change Research Program's Interagency Group on Integrative Modeling and the Joint Scientific Committee of the World Climate Research Program. Under his leadership, the GFDL has experienced remarkable growth on both the fundamental research side, in essence, creative science and innovation, and also subsequent deliverables to operational activities and applications. In particular, development of the modular ocean model, that is MOM, and FV3, a revolutionary atmospheric dynamics engine that delivers a seamless modeling system across time scales, have been hallmarks of the lab. FV3 is now the dynamical core for the operational forecasts of the National Weather Service, being selected as the winner in the first ever national competition. Both FV3 and MOM6 are being used at other national centers as well as by institutions abroad. These developments have enabled GFDL to be a world-leading institution in weather and climate modeling. He has received several prestigious awards in his outstanding career, notably the American Meteorological Society Henry G. Houghton Award 1994, three-time winner, co-winner of the World Meteorological Organization's Norbert Garbier MUMM International Award 1998, 2003, and 2013, member of the IPCC team that was co-awarded the 2007 Nobel Peace Prize, Walter R. Roberts Lecturer in Interdisciplinary Sciences, American Meteorological Society 2016, Distinguished Executive Presidential Award 2018, finalist Samuel J. Heyman Service to America Recognition 2019, American Geophysical Union Jules Gregory Charney Lecturer 2020, and the latest feather in his cap is American Meteorological Society Carl Gustav Rossby Research Medal 2022. Sir, we thank you for gracing the occasion. May I now invite the guest of honor, Professor Ramaswamy, to deliver the IITM Foundation Day lecture. Sir, you may please unmute yourself and begin the lecture.
Good evening. Can you see my slide?
Yes, sir.
Yes.
Okay, and can you hear me?
Yes.
Yeah.
Okay, thank you very much. First of all, thank you so much for the very, very generous introduction. I really appreciate that. And I would have to say good day, good evening, good AM, good PM, wherever you all are, and wherever people are tuned in on this very historic day, the IIT Foundation Day. This is a very great occasion to celebrate. I personally know so many of the people from the past at IITM and who have graced IITM, and it's really a pleasure to make the acquaintance of the present body of IITM, as well as especially the early careers and the younger scientists who are going to be the beacon and carriers the torch of the glorious past that IITM has had, and the wonderful present and the fabulous future that is in store for IITM. So really thankful to the organizing committee for inviting me to present this talk and to be a guest of honor. Really, really appreciate it from the bottom of my heart. It is a very, very great honor to me to be with you today. Respected Chief Guest, Professor Dadwal, very, very thankful to you for your kind words about GFDL, about Suki Banabi, the Nobel Prize, and then Joe Smagorinsky. Also respected Dr. Ravi Chandran, very nice to see you here. We've met so many times over the past. And congratulations to you on being the secretary of the MOES. And then Professor Krishnan, we've been meeting on and off so often in the recent weeks and months. So again, nice to see you, and congratulations on IITM's participation in the IPCC assessment. That's a really tribute to what IITM is contributing to the world body in science, in climate science. And then, respected colleagues and distinguished guests, I acknowledge each one of you for this very wonderful occasion, and I'm so thankful that I can make a few remarks about various aspects of climate science today. So I will now start my talk. And what so I was sort of I was thinking how to kind of present this talk, because you all are very well versed in climate science. I don't have to give a lecture on climate science, but I thought I would maybe give some perspectives, and they are personal ones. There are lots of different ways in which people think about how to cross the frontiers and advance the frontiers in climate science. And hopefully these are a few smatterings that are helpful to you as you contemplate the trajectories that IITM is going to take in the future. So I titled my talk in sort of taking upon three very latest things that have happened. One is, of course, the Physics Nobel, as you've already heard, 2021 Physics Prize, the Nobel Physics Prize. And then the conclusion of the IPCC 6th Assessment Working Group 1, which talks about the physical basis of climate change. And then, of course, this now unequivocal anthropogenic climate change declaration that's now appeared in at least the last three different IPCC reports, being strengthened with every assessment. And so I key off from that to maybe talk a few things about the prospects in climate science and how we can advance in science information for practical considerations. So let me begin with the IPCC Assessments Working Group 1 report. And I'm just going to go over sort of three major conclusions that were reached by AR6 Working Group 1. There's the first one. Recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. A very powerful conclusion about the impacts being already felt by the climate change. It is indisputable that human activities are causing climate change, making extreme climate events, including heat waves, heavy rainfall, and droughts, more frequent and severe. And this kind of goes to the heart of really making this impact not just global mean in extent, but also regional, and in the form of extremes, and all sorts of extremes, not just one kind of extreme, but you have all sorts of extremes occurring in different parts of the globe and at different times, and they're becoming more frequent and severe. And it's affecting every region on Earth in multiple ways. And the looking forward to the future, the IPCC AR6 now very definitively affirms that the changes we experience will increase as we go further in the 21st century because of further warming. Let me now dwell on the Nobel Prize, because what Suki Manabe did, and I think the whole world knows about it by now. I don't have to go into a lot of technical details about his career, about his pioneering career and the significant works he's done over his 40 years of research in NOAA, and then after that, continuing in Princeton. But I'm just going to capture some key aspects of his research, which laid the foundation of not just modern day climate modeling, but also understanding of climate science. I mean, what he brought into, what he did was open the whole field in terms of mathematical modeling of climate. And through that, answer questions of what things are the climate sensitive to and what are the impacts. And many of the findings that he did back in the 70s, 80s, 90s through his models have come true today. If you look at the pattern of warming, it's very much the same as what Suki did with a very, very simple global model back in the 70s and 80s. So one of the things that to me has been the kind of foundation of just modeling began with his 1967 paper, which is, of course, a paper for which he has been awarded the Nobel Prize, plus other awards. He's got other awards based on this very salient and very significant paper, which is the most highly cited paper in the geosciences. And this figure is actually the most appealing to me in that paper because it distinguished between relative equilibrium and relative convective equilibrium in the context of a one-dimensional model. It's a very important difference because the Earth cannot be in relative equilibrium by itself. You got to have convection, which takes away heat from the surface, deposits in the atmosphere. And the temperature structure that results with the conditions of fixed relative humidity is actually a very powerful conclusion, because prior to that, people knew about water vapor, and that you have evaporation on the surface, water vapor goes up, it's a greenhouse gas. But then people were confused about relative equilibrium and were drawing conclusions based on relative equilibrium, which led to a very unstable lapse rate in the atmosphere. And what Suki found and deduced actually from very few observations available at that time was that the atmosphere tends to conserve relative humidity and not absolute humidity. And so with conservation of relative humidity, he was able to deduce a temperature curve, which is actually very powerful because that is what happens. And his theory got him to get to the right conclusion, and he could explain it in very grand physical terms. Accompanying that was his calculation of what happens with doubling of CO2, and one of the most powerful results which stands still today. And all the 1D relative convective models built after that basically came to the same conclusion. He basically solved the problem of warming at the surface and cooling in the stratosphere. In fact, the 1961 paper was the first one which demonstrated why CO2 increase would actually cool the stratosphere while warming the surface. Something which, Suki is such a humble man. He never actually exaggerated. I mean, never really amplified that statement. But indeed, that is the first paper in which he shows and explains why the stratosphere would cool. And then Suki went on to build the global models. The very first coupled atmosphere-ocean model, which was a sector model, looked at the doubling of CO2 temperature changes on the entire, not just the 1D atmosphere, but a 3D land atmosphere, ocean. And what he found was this, one of the things that was very striking was, in addition to cooling of the stratosphere, warming of the surface, the amplification in the polar regions. And this, of course, is very prescient because that is really what's happening. The Arctic is cooling much more than the lower latitudes. Something which came out in 1975, and we are still trying to, just better the quantification from that work, but the pattern was set back then. Suki actually also did a couple of other things which were very notable. One was a paper which is not always highly highlighted as much as other papers, but Suki actually had a very coarse resolution model developing the warm cores associated with tropical storms. And then he did this calculation under doubling of CO2 to find out that the number of storms actually would decrease under increase of CO2, which is a little bit of a counterintuitive conclusion because you would expect warming of the SSTs to always increase the number of storms. But Suki found that the wind shear factor could actually decrease the number of storms, a result which holds true today with more complicated models. And then the other sort of work that I want to capture here is the long-term natural variability. Obviously, we don't have surface temperature records for hundreds and hundreds of years, which would then give a very nice view into the variability of the Earth system. But what Suki did was he said, let me try to capture the variability as far as observations go, which was only a few decades, and actually several decades, and then said that let me see if a model reproduces that variability, and then run the model 1,000 years to see if what the model's natural variability would be, because he wanted to kind of see if this rise in temperature, and this is a paper back in 96, whether this rise in temperature is going to be captured by the amplitude of variations in the natural system. And he found that indeed it won't. The rise in temperature cannot capture that. So that's kind of something, again, we are doing today with models running lots and lots of years so that we capture the natural variability.
Pardon me, sir.
Yes.
Sir, can you minimize a small window that is appearing on the bottom side?
Yeah, how do I do that? I've been trying to do that. Okay,
yes, yeah.
Okay, go
yes,
on. Sorry about that. I was trying to see how I could get rid of it. Thanks for suggesting that. Okay, so let me get to the present day. So we know now a lot about forces of climate, the factors, but there are also outstanding issues, and that's kind of where I think we have to focus attention on. So this is the Earth system. I don't have to dwell on it. IITM also is pursuing these ideas with both the physical system as well as the ecosystem. And of course, we rely on high-performance computers to basically do this mathematical modeling of the Earth system and solve it on the computers. This is the forcing of climate change. It's actually from the previous IPCC, but doesn't matter because what I want to dwell on is the fact that the greenhouse gas forcing, and to the right of this line means warming, to the left of this line means a cooling tendency. So that greenhouse gas forcing is one of the positive factors. And then you have aerosol forcing, which is kind of confounds the actual forcing, because net forcing, because it's got positive and negative contributions, with the negative contribution generally winning over. But it's, as I'll come to in the later plots, it is rather uncertain. You see the uncertainty bar being very large, so that the net forcing, which is this red bar here, is positive, but has a large uncertainty because of the presence of the aerosol. Now, the things about aerosols are kind of twofold. One is just the spatial and temporal inhomogeneity in them. So this is actually a simulation where you're seeing dust enveloped in vortices, which are later going to form hurricanes, possibly. And the dust is mixed in with the water vapor in the clouds. And that creates, and since both of them are relatively active species, we have an issue with how to deal with this. And the physics of it is still not very certain. And one of the things that makes it uncertain is all this stuff that's shown on this figure. Because when you have aerosols and clouds, particles and clouds, and then you are mixing in with boundary layer processes and convection, deep convection, shallow convection, you have lots of uncertainties concerning each one of these processes, including the scales on which they occur. So if you look at the scale, this is 50 to 100 kilometers. And over this small scale, you have lots of things happening, and which has ramifications for the larger scale. So this larger scale interaction with the complexities occurring on the smaller scales really starts to hurt our quantification of both climate forcing and thus the resulting climate response due to aerosol pollution as well as changes in convection. Nevertheless, I want to kind of draw a picture to what we have been able to do in terms of attribution. And this is a little bit old. It's a 3-year-old paper on the attribution. But the key point is that what you're seeing among the black and red curves are the observations of the anomalies in surface temperature. And then if you take, for example, this particular panel, the top right panel, you see from all the CMIP5 models, natural variability. So this is done in the same way that Suki Manabe did it with the earliest model. And you see that the observations are exceeding the natural variability. So that's a very clear sign that natural variability cannot contribute to the observed rise in temperature. And then the other panels, but I'll just go to this one, which includes models with all the forcings, natural and anthropogenic. And you see that the envelope, so that the mean of the models, captures the observed temperature change very well, which then leads to the strong conclusion from IPCC that it's the anthropogenic influence that has caused this rise in temperature. So on the attribution of the global mean, we are fairly clear on what's happening. And of course, associated with warming, there are all sorts of other indicators which are also pointing to warming, giving multiple lines of evidence. So it's not just surface temperature. There's multiple lines of evidence. So in addition to surface temperature, you have humidity increasing. You have temperature of the lower atmosphere increasing. You have temperatures over both land and oceans increasing. Ocean heat content is increasing. And accompanying that, global sea level is increasing, mainly due to the expansion of water, thermal expansion of water. Then you have also accompanying them snow, glaciers, and Arctic sea ice retreating. And so these are now the evidences which compel us to no longer question the fact that this is due to anthropogenic influence, and therefore the upshot of this is that the further increase in greenhouse gases is actually going to exacerbate the warming. So let's see, I'm going to talk about the future a little bit, about what is in store in future, present and future, and therefore the prospects. So we have a lot of uncertainties, but there are also bright prospects for the future. So one of the things when we talk about the future, there are sort of three things that are very important. One is the resolution. Obviously, the greater the resolution of the model, the more information you get. The complexity of the problem, how do you represent the complexity and how effectively do you tackle it? And quantifying the uncertainties, mainly sort of, for example, through running large ensembles. So these are sort of the axes that we always have to deal with. And what I'm showing you now is a global cloud resolving model at 3 kilometers. This is sort of now, this is just the atmosphere. But what we are trying to do now is to develop this into a couple model at 3 kilometers. Of course, this consumes a lot of computing, so which is something that we're always thirsty for. But if we get the computing, then I think this is going to be the future of climate models, where you're running the atmosphere at 3 kilometers. And what you see here is very nicely the circulation in the northern hemisphere, southern hemisphere, mid latitudes, tropics, high latitudes, and very realistic. And I'll show you in the sort of the next figure the comparison with a satellite image of this GCRM simulation. So on the left is the model, the right is the satellite. And just visually, it's going to be very hard. If I didn't tell you which one was model, which one was observation, it's going to be very difficult to settle the question of which one is the observation. And this is for a particular day. So this is actually a weather forecast simulation, but it's a very promising avenue that we have in terms of going to high resolution and actually capturing the atmospheric circulation very well. So just like the atmospheric circulation, we also have to go to high resolution of the ocean. This is an animation of the Gulf Stream with very high resolution model. I think it's 1/12 of a degree model in the ocean. And it shows you how you can capture all these very, very fine scale things happening, especially near the coastlines, which is proving very important now, not just for the ocean circulation or coastal circulation, but also for the marine ecosystems along the coastlines, because they depend on this circulation, the upwelling, the flow from going from south to north, and then the vortices, which carry, of course, heat, and of course, in the various ocean basins, you have the carbon uptake also happening. So this is again sort of a very good prospect for the future, where you can do process studies, you can do regional climate impacts, especially because coastal circulations in the ocean affect the weather, especially inland. And then, of course, high spatial resolution information, particularly as you go to the ecosystems. And then one of the things that accompanies modeling, and I think observations were brought up earlier, which is very important because the observations and modeling have to be synthesized and integrated together. And what you see here is a sort of a cartoon where now it's no longer just the surface temperature metric or Earth radiation budget metric that's important, but really everything. The jet stream movement, the atmospheric circulation involving tropical air-sea interactions, MJOs, and then the oceanic circulation involving something like AMOC. How are they all captured in a high sense of fidelity in the model? And for that, you need really fine observations, satellite as well as ground-based, and then field campaigns to be able to actually check out these high-resolution models that are coming online and what they are they able to express the fidelity not just in one aspect of the Earth system, but really in multiple aspects of the Earth system, which then builds up confidence in the impacts on various things like ecosystems. By the way, how am I doing on time? I kind of have lost track of time. Can someone tell me if how many minutes I have?
Sir, it is okay. I mean, you are on everything.
You
is
have
on time.
enough time.
Just let me know. Just let me know if when I'm like 5 minutes to deadline or something like that.
Okay.
Thank you.
Yes.
Okay, so now going into projections and predictions. So this is now the most important thing. One of the things that IPCC has settled is the question of how the warming is going to be. There's no doubt about it. It's going to increase until some net zero emission trajectories really take place. But then what after that? I mean, we know that the Earth is warming, but now comes the issue of projections and predictions. Now, this is again from the previous IPCC, but it shows if you see just for example, the right-hand side column, which is the temperature projections under various scenarios, the four rows of various scenarios. Bottom line is the least aggressive scenario. Up the top is the most aggressive emission scenarios, and so obviously the more the emissions, the more the warming, and you see the polar amplification. The most warming is the higher northern latitudes. Land is warming faster than oceans, and the northern hemisphere is warming faster than southern hemisphere. All actually some things that Suki Manabe did that with some of the very old models. But this is sort of happening, and accompanying that is the heat wave issue, namely that heat waves will occur with higher frequency and duration as the Earth warms. So that's like a phenomenon that affects at the very human level. It's not just the global mean or area-wide temperatures. One of the things that we've investigated with model resolution is shown here, which shows the annual mean precip over the continental United States. And this is a very characteristic feature of the United States in terms of, if you see from the top left panel, which is the observations, there is much more rain in the eastern half of the US than in the western half. And as we go, and so if you look at a model back in 2006, this was a picture we had. You can sort of say it's roughly comparable, but on a local level, it's pretty useless because it's very, very broad, very coarse. This was 160 mile tiles. This was 34 1/5 of the resolution from this one. So you see the increasingly finer pattern. And then this is actually even a 5-year-old model. But as we go to higher resolution, you start to capture the orographic influence along the west coast, the relative dryness over the western half, and then even sort of the wetter southeastern United States. So the high resolution does capture a lot of features, but of course you got to be careful that it's not garbage that you're reproducing at the local level. So the large scale circulation does matter, it's representation, but definitely the high resolution gives you information which is at the regional levels, which is more useful, of course, for managers of various sectors to be able to manage the situation. And then in sort of recent times, we have now a SPEAR model, and I'm not going to expand the acronym, but it's the seasonal prediction model we have. And one of the things that you see here is a scale in predicting the Arctic sea ice, summer sea ice extent with lead time. So the sort of predictability is actually quite good in terms of 2 to 4 month lead time with the SPEAR model. And then another interesting thing that has come up with this model is the atmospheric rivers, which is the flow of moisture into California and the west coast of US during the winter to springtime, because that determines whether California is going to go through a dry phase in the summer or not. And this is a reproduction of actually the brighter spots are where you see these channels of atmospheric moisture, high moisture, coming in and then hitting the west coast of US and dumping moisture. So this is actually now predictable about 8 to 10 months in advance, which is something we never expected, but it looks like predictions can be, in some cases, can be we would be able to do that well ahead of time. Another thing that's captured with the SPEAR prediction model is the snowpack. And this is actually the observed is on the right-hand side, predicted is on the left-hand side. And the browns denote below average snowpack, which is very important for the hydrometeorological resources in the west of western US. And you see the representation by the model in terms of prediction made on July 1st of the previous year. So this is 6-7 months in advance. This is very sort of encouraging that we can actually do this. And so this is sort of another plus, if you will, in terms of advances in modeling. And then very recently, we've constructed the AMOC both from past to present and to the future. There are very few observations, of course. This is the extent of observations we have. But all evidence is, and this is a large ensemble. So there were 30-member ensembles done with both a low resolution atmosphere, 100 kilometers, and a medium resolution, 50 kilometers. Our high resolution is going to be 25 kilometers, which is still going. And you see kind of the reproduction of the observation of the extent they are there, and then the prediction into the future in terms of what is going to happen to AMOC. This, by the way, a lot of models actually do predict this slowing down of the AMOC strength. And then, as you may have read, there's a lot of things accompanying drought and dry vegetation especially in the western U.S., and that is the fires over California and the spread of the plumes. So this is actually a weather forecast model, a very high resolution model, which runs, like like the WRF model, and it's capturing the fire spread. This case, a particular California fire in 2018. And then the longer time scale is the Alaskan fires. And what you see here is fire carbon emission, kind of an indicator of the amount of carbon that's emitted from fires. The red lines are the recent observations. That's all the observations that exist. The black line is actually simulations from a model. And what you see is that the model is actually starting to simulate a higher frequency of fires as you come towards the end of 2000 and into the 2000s. And this is because Alaska is warming up very, very highly in the summertime, and that's raising the issue of fire. So again, the model with the Earth system model, so this has carbon interacting the climate, and that is able to kind of reproduce, qualitatively at least, the fires. But now the bigger issue with anything like this, fires, is the whole Earth system, where you have agricultural waste burning, you have forest fires, you have natural fires, natural and anthropogenic fires, lightning, human activity. And then that has a whole cycle which kind of involves smoke lofting, moving about, affecting atmospheric composition, and then deposition on both land and ocean. So this whole cycle really has to be dealt with our system models. We are still not there, but it is something that is being thought about in the community. And finally, let me come to the sea level rise. So this is from the recent IPCC showing the sea level rise under various scenarios. You have, of course, this prospect: if there is a large instability in the ice sheet, then the sea level rise could be even greater than any of these scenarios, even the SSP 8.5 scenario. But so sea level rise is going to happen due to the expansion of water with warming, but also due to ice sheet melting, and that's the part which we're not certain about. But there's one more thing that I want to point out with the sea level rise, which is again extremely relevant to regional populations, especially along the coastlines, and 50% of the world's population lives along the coastlines. So this is actually a depiction of a simulation where we are examining the storm-related extreme sea level to combine weather and climate forcing. So climate change is giving you rise in sea level, but then there were storms happening over near the coastlines are just causing coastal inundation, and so they are important on top of the sea level rise. So what you're seeing is simulations of what's happening to the coastlines in New York, Miami, New Orleans for one-time CO2, which is kind of the blue line of uncontrolled, unperturbed state, and the red line is doubling of CO2. And as you can see, in a place like Miami, and the purple line is 1 in 10-year event. So in Miami, for example, the 1 in 10-year events don't happen with the normal CO2, pre-industrial CO2. But when you double CO2, you start to cross that 1 in 10-year line, meaning that you have more propensity for storms in the warmer climate. Now, in contrast to Miami, New York has much more variability. The blue lines are much more variable, also red lines. And that's because New York is much more affected by the synoptic scale storms. Miami is affected only, of course, during the hurricane season, but not really other times of the year. And so in this case, the red line is there are excursions, so you can cross the 1 in 10-year line, but it comes much later in New York. New Orleans is very interesting because it has so much variability due to storms coming over that even in the unperturbed state, you can cross the 1 in 10-year mark. So this is what happens. The sea level rise is even if it is the same, it's not the same in all these three places. But even if it was the same, the synoptic scale events can cause you perturbations, which are actually of societal concern. So that's kind of what this is depicting. And so now we have to consider things with combined weather and climate implications. It's not just the climate change alone, it's the weather extremes occurring on top of climate change. So now let me just end with a few slides on the societal context here. So as I just mentioned, weather extremes and climate change is now what the problems are. because climate change is happening. So no question about that. The forcings due to greenhouse gases and the drawdown of aerosols is going to exacerbate all the long-term climate change. But we have weather extremes. How does the atmospheric and ocean circulation change with this climate change? And how does it change? I mean, what is the trajectory? Is it something abrupt? Is it going to be something irreversible? That is, even if you have net zero emissions, at some point, are everything that you are seeing now is reversible or not? And so for that, you need the high resolution models. You also need observations. So I'm kind of not been dwelling on observations, but that's important too. But what we are trying in NOAA is to build seamless high resolution modeling system, because you have to have the same physics going on the weather timescales as for the climate end of the modeling, because it had to be consistent. So that's the catch here. So with the high resolution seamless models, what you want to do is not just capture the frequency of occurrence and the location, but also the severity, duration, and even early alerts. One of the questions is, how early can you predict something? If there is predictability in the system that you can predict several months in advance, that's so much more better, because society gets very advanced information to adapt and mitigate. And then, of course, there are multiple extremes. So it's not just sort of the hurricane happening, but it's the long-term coastal inundation, recovery of the coastal lines, or if you take heat waves, then there's downstream effects of atmospheric pollution. If you take fires and droughts, that has long-term effects into not only the physical aspects of the system, but also the ecosystems, including the human ecosystem. And one of the things that we've been doing with the Earth System Model is this chlorophyll prediction scale, which is sort of giving you an indication of what the marine ecosystem might look like, because this all of course happens where upwelling occurs. And so the prediction skill here is actually something like more than 1 month, it's actually a season ahead, which is again very encouraging that in at least some parts of the ocean, the predictions can extend to several months, and in some very specific regions, you can actually go up to 1 year in advance in terms of prediction. In terms of relating all the things we are doing in the climate science side, the ultimate success is going to be if this is able to communicate and interact with the sector of society that actually are going to make use of this information and make for better living. So here is a thing that in the fisheries, and since NOAA has mandate over fisheries and weather, it has this mandate of trying to do the connection across. And this is one way to look at it. This is a spatial scale here, and you look at the various systems, weather systems occurring on the various spatial scales, and then the time scale going from days to century. And what is in the colored ovals is the fisheries industry's various considerations. So industry operations and monitoring and closures are on a very short time scale, catch limits on the annual time scale, and then rebuilding plans and capitalization and resilience and sustainability are being considered over decades or centuries. So in a sense, this is kind of the connection that we feel other sectors may want to consider similarly, maybe not in the same fashion, but in other fashion, to actually bring the science down to societal concerns. And just schematically, what kind of we are very successful in looking at are the weather and climate events leading to risks. But there's also things like vulnerability, which is the predisposition of a population to be adversely affected, and then exposure, being in the wrong place at the wrong time, namely, how often humanity is exposed to weather and climate events, and all that goes into the calculation of risks, which of course then feeds on to climate investments, infrastructure, adaptation measures, and mitigation measures. And finally, I normally do not use newspapers and articles in newspapers to inject it into the scientific talks. But this one, which came out in New York Times just a few 2 weeks back, was kind of impressive in the sense that it was showing how if no policies had been enacted, we were well on our way to warming of nearly 4 degrees by 2100. Now, because of current policies, thanks to rapid growth in clean energy and some action on the mitigation side, we are not going to 4 degrees, but probably about 3 degrees. With pledges, it comes down even more. And these are pledges, so that's not necessarily action. But if countries keep to that pledge, then it's 2 degrees. And this is a 1.5 degrees, kind of what the trajectory would be for the global mean temperature. So an indication of how, things have evolved over the last, especially, let's say, 30 years. Rio Convention was, 1992, 30 years ago. So a lot of advances have taken place, but probably a lot of people will argue that not fast enough. And that certainly is true. So even though it's just a schematic here, I think it's very telling as to how we've advanced and how we've not advanced in terms of taking action against reducing the prospect of very warm temperatures. All right, I will end there, and thank you very much. And I am happy to take questions and comments. And I'm wondering how to get back. Okay, I think I'm back. Okay. Thank you very much.
Thank you, Professor Ramaswamy, for such an enlightening and comprehensive lecture. It is our pleasure that you joined the event and bestowed us by being the guest of honor. Sir, as I can see, there are no questions on the YouTube live chat box. So with this, may I now request Dr. Krishnan to say a few words and declare the awards for the 60th Foundation Day?
Yeah. Thank you, Bhupendra. First of all, many thanks to Professor Ramaswamy. It was a beautiful talk. I really enjoyed. The kind of impacts, the impact of climate change on weather extremes and the way you are modeling in GFDL is very, very impressive. I was wondering whether you have some sea level projections for the Indian region and their effect of their changes and how they are going to how the storminess is further going to affect the inundation of coastal areas in the Indian region. I was wondering if there is some slide that you would like to highlight.
Yeah, we've just started looking at looking at other regions of the world, including the Indian region, both on the Arabian Sea side and the Bay of Bengal side, and including the coastline of Bangladesh. It's one of the things that happens is that the weather circulation, you have to, the control simulation has to get it right, and over the Indian region that's a bit of a problem because we still have to deal with the monsoonal circulation, and so when you're talking about weather, it's really got to be. It's really not enough to get the monthly means right for the weather. You got to get it daily because you are looking at daily sea level rise, sea level anomaly. So a bit of a challenge, but yeah, we are working on that. We're working. That's proving to be a little bit of a difficult region because of the atmospheric circulation.
Okay. Yeah, and one more question. You showed the global model simulation at 3 kilometer cloud resolving model. So I was thinking, how long is that simulation?
Yeah, so till last year, we were able to do only like month-long simulations because it requires a lot of storage. There's a issue of not just computing, but also data storage. But we've been using machine learning techniques to kind of advance the saving of the data a little bit. So this year, actually, for the first time, we've completed a year-long simulation, full 1 year long simulation. And it's actually now on to 3 years. The second year has been done too. But we are hoping that, hopefully with this, with some of the bills going in Congress, that there'll be an enhancement of computing. And we really want to do long-term integration, like at least going to 50 years with the GCRMs. It's actually very, very nice. I mean, I think this is the way to go. And it's not anything bad. I mean, it's actually giving very good simulations. The problem is computing aspects. That's kind of where, and we are, again, if the enhancement in computing that we think we are getting comes through, then we can actually even do a coupled model. And what we are doing is, I don't think we can get to 3 kilometer atmosphere and ocean at the same time. But the ocean would be a little bit coarse. But what we are hoping is that we can do something like a 6.5 kilometer global atmosphere with a 3 kilometer nesting over portions where you want to examine the impacts in particular. So that is going to be affordable with like a 1/8 degree ocean. So that's kind of how, we got to kind of do this in a hierarchical fashion. We don't think we can jump directly to a 3-kilometer atmosphere and ocean. It's going to have to be in stages, but we are very hopeful of that. I think there's the success of this, both the GCRM as well as the regional MOM6 models, ocean models, is actually very encouraging in terms of pointing to the fact, at least, that we have prototypes which are working. So the next stage is just to just to kind of plan out how you can do the full simulations over long-term periods.
Yeah. And lastly, Ram, one question I have. Still, many models are having problems with the tropical convection and how they organize on very large scales. So some people are advocating that this kilometer scale model, cloud resolving model, may be the solution. But it's, as you said, it's computationally so demanding. How do we go with moderate computer requirements? How do we handle this kind of
complex? So one of the things we are exploring in partnership with Vulcan, a private sector philanthropic foundation, one of the things we are investigating is how we can deploy artificial intelligence, machine learning in particular, to give you a shortcut through the higher resolution simulation. So, one trick is you use the GCRM simulation. Actually, that's how the GCRM simulations are being used for the very first application has been this, that you run it every month for 30 days. So, you start with every month, run for 30 days. So you have the whole year statistics. And then you build up a sort of a catalog of machine learned data on a coarser resolution. So you use that 3-kilometer scale moist simulation, moist processes like, moisture, low-level convergence, upper-level divergence, and you now take it to something like a 25-kilometer climate model. So it's literally parameterizing based on the GCRM and applying it in a 25-kilometer model, which is, coarse, but not too coarse. It's actually a pretty high-resolution climate model. And we're investigating how that works in the context of a 25-kilometer model's atmospheric circulation. Turns out it is not too bad. I think there are some regions where, it's not, high latitudes is a little bit of a problem. Low latitudes actually is pretty good. The simulation of convection, deep convection, shallow convection is actually not too bad. So it's a bit cumbersome because you're translating from one scale to another scale, but you're making use of the highest resolution that you can run at the regional scales, and then transferring that information seems to work. But I think the proof is still going to be when it's not just what you translated that works, because that is guaranteed to work, right? You're translating something known to even if it's a coarser scale, you make it work. But other parameters, like how does it affect, downstream of that? How do teleconnections work, for example? That part, is still a question mark. It's still got to be verified.
Yeah. Thanks a lot, Professor Ramaswamy. It was excellent. Very inspiring talk.
Thank you.
Thank you for accepting our invitation. Great
pleasure. Absolute pleasure.
Can I ask?
Sir, there is one question from Dr. Mukhopadhyay.
Okay.
No, I just want to that this 3-kilometer resolution, 3-kilometer GCRM, is it based on FV3 GFS or is it?
Yes.
And my another question is that when we go to this cloud resolving global model, do you feel that how can we run an ensemble of GCRM? Do you feel that?
Actually, we do run 5 simulations of the GCRM. So it's not just one that you're seeing. You're seeing a have an ensemble for 5. Obviously, we would like to run 30 to 50. That's kind of the number you want. That's unfortunately, we are not able to do it here. And that's a desirable, very high desirable. We can't do that right now. But that is going to be something that's definitely going to be possible in the future. A lot of people have GCRMs now. The fine resolution, 6-kilometer, 3-kilometer. So I'm sure that computing, is going to increase. Computing resource is going to increase. So we are going to be able to get to that. I know we can't get there fast enough. That's the problem.
Thank you.
Sir, there is a question on YouTube chat box. Dr. Ashish Kumar Mitra is asking, when the NCEP's FV3 based seamless coupled model for multi-week forecast will be operational?
I don't have the timetable in front of me, but I know that sub-seasonal, so week, I think the question was about multi-week, but I don't know about multi-week, but sub-seasonal is, I think they're talking about fiscal year 24, which means, end of 2023, beginning of 2024 is when they expect to go operational.
Okay.
Thank you, sir. There are no more questions on the YouTube chat box. So we thank you, sir, for your lecture and for giving such an enlightening talk.
Yeah.
Very welcome. My pleasure.
Yeah. Thank you, Professor Ramaswamy. It was very, very inspiring to know the journey entirely, starting from Professor Suki Manabe's contributions, the IPCC latest assessment report, and the fantastic work that GFDL is doing in modeling, and the way they have reached is extreme computing, and it's very, very impressive. And so we look forward to having collaborations with your institute, and because these problems, what we are facing with climate change and extreme weather, it's happening everywhere. So I think this requires a collaborative mechanism if we want to really enhance the science and connect the science to operations. It needs to go to a completely different level, and we would very much require your guidance and support from GFDL. And thank you very much, Ram, for this.
Yeah, thank you. I look forward to the continued partnership with IITM as well as other institutions in India, where we've had very fruitful collaborations and partnerships advancing the frontiers. Thank you.
Thank you so much. Yeah. Also, I want to thank our chief guest, Professor Dadwal, I think for making important suggestions about the future challenges that we need to address in terms of recruitment, human resources, and the complexities of modeling or a region like Indian region or the monsoons, and the importance of land surface process and so on, and the development of skilled human resources for the sensor development for the observations. I think he made some very important recommendations. Thank you very much. And also to our secretary, Professor Ravichandran, for all his guidance and important suggestions that he gave to address, we have made progress, but there are also a lot of challenges in terms of parameterizations and how to improve them, and also increasing the resolution and for the observational programs. So once again, I want to thank you all, and also Partha, Bhupendra, and Smriti for all your support, and all the IT personnel. So we can move maybe to the next part of the agenda. Actually, we are a little ahead of time. We are almost 30 minutes ahead of schedule.
Yes, sir.
Yeah.
Sir, maybe you can declare the awards.
Okay. Yeah. So now we are in the final part of the agenda, today's agenda. I will just declare the list of awardees, various awards for this Foundation Day. The Professor D.R. Sikka Best Student Award for 2020 is shared by Sri Ushnansu Datta, IITM Senior Research Fellow, and Sri Panini Dasgupta, IITM Senior Research Fellow. Let's give them a big round of applause. The Best Employee Award for the Scientific and Technical Support Staff category goes to Srimati Swati Atle, Scientific Officer Grade 2. Let us give a round of applause to Swati Atle. The Best Employee Award for the Administrative Staff category goes to Srimati Bhavana Nayak, Senior Executive. Let us give her a round of applause to Bhavana Nayak. The Hindi Rajbhasha Puraskar goes to Sri Bhupendra Bahadur Singh, Vaigyanik D. Srimati Sunita Karbanda, Sahayak Prabandhak. Sri Shafi Syed, Varisht Karyakari. Sri Sachin Gayakwad, Varisht Karyakari. Let us give them all of them a big round of applause. The Outstanding Performance Award goes to the Account Section, the Computer Division, Sri Padmakar Domutwar, Assistant Engineer, Audio Video, who has also supported us for today's event. Sri Suresh Nivalkar, Office Boy. Sri Krishna Gote, Housekeeping Staff. Let us give them all a big round of applause. And finally, Dr. Guman Singh Meena, Scientist. He has completed 25 years of valuable service to IITM. So we'll also thank Professor Guman Singh Meena for the successful completion of 25 years of service to IITM. And finally, the Professor P.R. Pisharati Award and Professor R. Ananthakrishnan Award will be given later, will be declared later. So with this, I come to the end of all the list of awardees. Thank you all.
Hearty congratulations to all the awardees on your achievement.
Yeah.
Now I invite Dr. Mukhopadhyay.
Yeah, hearty congratulations to all the award winners. And we encourage them to keep up their good work and keep doing excellent work. Hearty congratulations to all the awardees. Yes.
Yeah. Now I invite Dr. Mukhopadhyay to deliver the vote of the thanks.
Thank you, Shruti. Respected Secretary, sir.
Sir, you are not audible. It's muted.
Is it okay now? Is it okay?
Yeah, yes, sir.
It's okay, sir.
Okay. Respected Secretary, MOES, Dr. M. Ravichandran, Professor V.K. Dadwal, Professor V. Ramaswamy, Dr. R. Krishnan, all the scientists of IITM and scientists of ex and present IITM employees, scientists of all other MOES organizations, scientists of MOES, all our friends and colleagues, and ladies and gentlemen. Firstly, I join Director and everyone to express our best wishes and congratulations to all IITM family and fraternity on this great occasion of 60th Foundation Day of the Institute. We are particularly grateful to Dr. M. Ravichandran, Secretary to Government of India, MOES, for kindly accepting our invitation and gracing the occasions and giving very, very important suggestions and guidance in spite of his extremely busy schedule. Thank you, sir. We express our sincere thanks and gratitude to today's chief guest, Professor V.K. Dadwal, for kindly accepting our invitation and gracing the occasion as chief guest of the function and giving a very insightful talk, sir. Thank you very much, sir. We sincerely express our thanks and gratitude to Professor V. Ramaswamy for accepting our invitation and giving a very, very important and very interesting talk. And delivering and be present as guest of honor. Thank you so much, sir. We express our sincere thanks and gratitude to Dr. R. Krishnan, Director in charge IITM, for constantly guiding us and supervising meticulously all the micro details of the arrangements. We are also grateful, like to put this in record, we are really grateful and acknowledge the continuous support of Ministry of Arts Science for this enormous advancement and journey of IITM in these 60 years. And our heartiest congratulations to all the awardees. And our gratitude also goes to admin officer, account officer, and all the teams of administration, general administration, computer, particularly Padmakar, library, and all the sections and divisions for the great support and cooperation in making today's function a great success. And finally, thanks are also due to Bhupender Singh and Ms. Rati Gupta for excellently coordinating the function since morning. Thank you so much.
Thank you, sir.
Thank you, everyone.
With this,
And,
we now, yeah, sir, you want to say something?
Yeah, so final thanks to our secretary, Dr. Ravichandran, our chief guest, Professor Dadwal, and our guest of honor, Professor Ramaswamy, all the participants, and all the delegates and all the people who helped us in organizing this event. And congratulations to everyone, and happy 60th IITM Foundation Day. Thank you, one and all.
Thank you.
Thank you, sir. With this, we now conclude our 60th Foundation Day program. Thank you again for your presence. Thank you.
very
Jai
much.
Hind.
Thank you, Jai Hind.
Thank you.
Thank you. Bye.
Namaskar.
Bye.
Bye, sir.